All right, so we're going to do the first half of Doppler. Okay, buckle up. So Doppler. So for Doppler, you have something called the Doppler shift or the Doppler frequency. So they both mean the same thing. The reason why it can also be called Doppler frequency is because the formula has units of frequency in it. So when 'cause there's a formula behind this, so when the machine does the math, the units are frequency. It then gets converted into a velocity, which is what we see. Because if you just give us a frequency, we don't really know how to take that. But if you give us a velocity, then we're more familiar with that. We can work with that better. So just be aware that it could be called a Doppler shift and a Doppler frequency. I like Doppler shift because a shift is like a movement. Okay. So Doppler shift to Doppler frequency refers to movement. Now, this is the biggest distinction that I kind of just want you to know, not necessarily for the SPI, but I think it's good to just have this in your mind because it just makes you think about things a little bit differently. The machine is seeing a movement, okay? That's it, a movement. When we use it for blood. Blood is moving, okay? Don't get me wrong. But to the machine, it could care less. It doesn't care. It doesn't know that it's blood. It just knows it's something that is moving. That's it. Okay. So the machine is not here to make any distinctions. It isn't here to use logic and common sense. It only does math. Okay. And then when we get into angles later, you'll see how you can trick the machine into thinking something else. But it only knows math. All right. We use it for blood, but the machine just says, if it's moving, I'm putting color on it. Okay, that's why sometimes you see color in really weird places. And you know that there's no blood there. So why do I see color? Because we assume if there's color, there's blood. That's what we assume. But no, the machine says if it's moving, I'm putting color on it. Okay. So I just want you to know that. Okay, it's a movement for the Doppler shift. Now the concept is things moving together or things going apart. Okay, moving towards me or moving away from me. So the first formula is the Doppler shift formula. It's this simple formula for the Doppler frequency that says reflected frequency minus transmitted frequency. It's a very simple formula, so chances are you're not going to be tested on it. They're going to test you on the super complicated one, okay? But it's good to know this just in case, okay? Chances are that won't happen, but just in case. And the way that I remember this is that it's in alphabetical order, D, R, and T. Because when I was studying this for my exam, I always used to have a hard time remembering, is it transmitted minus reflected, or is it reflected minus transmitted? So the only way that I eventually was able to remember it was through repetition, but also just remembering that is everything is alphabetized. D, R, T. You know, R comes before T in the alphabet. All right. So let's do a little bit of math here, which you're not going to do in the SPI, but is to prove a point. Transmitted is what goes into the body. Okay. That is what leaves my transducer. So let's say that what leaves my transducer is 5 megahertz. And let's say that what came back from this moving, let's just call it blood, right? Since we're going to be pretty much just only talking about blood. Let's say that the blood, this 5 megahertz hit the blood, and then the blood created a reflection. And that reflection was a 5.1 megahertz. So it was higher than what was sent out. And if I do the math, let me erase this. Do the math, my answer is going to be 0.1 megahertz. Okay, that's my answer, 5.1 minus 5. Now let's do another example. I also sent out 5 megahertz, but in this case, I received 4.9 megahertz as my reflection. Okay, so if I do the math here, it's also 0.1 megahertz, but in this case, it will be negative 4.9 minus 5. Okay. So here's a very important distinction. The signs, the positive and the negative signs, right? In our world, positive and negative are very different things, right? Like if we talk about finances, being in a positive is fantastic. Being in a negative is very bad. Negatives are so bad that I rather have $0 in my bank account than have negative $10 in my bank account. That's how bad negatives are, that I'd rather have 0, okay? The only difference between 0 and negative 15 is that one you're broke and the other one you're broke, okay? But either case, we say, man, I'd rather have 0. I'd rather be broke than broke. So that's how we view negatives and positives. With the Doppler shift, that is not the case. Okay, so you really have to go through a little bit of a paradigm mental shift when it comes to this. Positive and negatives in the Doppler shift only give you one thing, and that is direction. That's all they give you. They do not make one number bigger or smaller than the other. So notice in this example, it's positive 0.1 megahertz and negative 0.1 megahertz. Okay. If I ignore the signs, the numbers are identical. Okay. That means that these two numbers are equally as fast or equally as slow. I don't know if this is a small shift. I don't know. But they're equally as fast or equally as slow. The only difference is one is towards me. So the positive is towards, and the negative is away. That is the only difference between these two numbers. That one is towards me and the other one is away. But one is not faster than the other because the numbers are identical. Okay. If the numbers were different, then the bigger number will be the faster number because, you know, faster implies is a bigger number. So that would be different. But it wouldn't matter because if this is negative 0.5 megahertz, then this number is bigger. So in this case, this negative is faster than this positive because we're just looking at the numbers. Remember, we don't look at the signs. The signs is only for directions. Okay, only for that. Because the machine has to communicate with you somehow that if something is going towards you or away from you. Okay, and the way it does that is with these signs. All right. So when you look at a spectral wave, and the spectral wave is like this one is faster than this one. Because look how much bigger it is, the one at the bottom. Okay. So the one at the bottom is faster than the one on top. Okay. Even though the one at the bottom is negative. But again, negative doesn't mean anything besides direction. That's all it is. It just gives you direction. All right. So from here on out, just because something is below the baseline and it makes it negative, doesn't mean that it's somehow slower or inferior. Okay. It just means a different direction. And this is the way that the machine communicates to you. Hey, look, this is going a different direction. Okay. So you're going to hear a lot of driving examples because driving is movement. And I always tell students, couldn't someone be coming slowly towards you, driving slowly towards you, and couldn't somebody else be driving really fast away from you? So it's like, what's the difference? Why would this person who's driving away from you be slower than the person coming towards you, you know? So I think it's mostly aesthetics that we see like a wave below the baseline and we think of it as it being inferior, but that's not the case, okay? And when we get to aliasing, I'll bring it up and I'll tell you, you can have aliasing away from you. Why not? Things can move fast away from you, so you can have aliasing away from you, okay? So this positive and negative only imply direction. That is it. If you want to know which one is faster, then you have to look at which one has a bigger number. Okay, and that's it, not the sign. Um, then the book wants you to know that you have speed and you have velocity, and that velocity is what we use. Okay, so for speed, you have something like 50 miles per hour. And for velocity, you have the exact same thing, except that you're going to give it a direction. That is all velocity is. The velocity is speed. Okay, velocity is speed with a direction. Okay, and every time we use Doppler, we always have a direction. If you look at color, right, you start using color, that color already implies a direction, is either towards you or away from you. If you look at your spectral wave, if you see the wave above the baseline, that's a direction, it's towards you. If you see a spectral wave below the baseline, that's away from you, that's also a direction. So anytime you use Doppler, it automatically gives you some sort of speed, how fast something is going, but at the same time, it gives you a direction. So the moment that that happens, they call it a velocity. Okay, so velocity is simply the addition of the direction, which we always see in Doppler. Now here's the long formula, okay? And I write it very short. I don't write like all the terms, I just write the letters. So the Doppler shift equals 2 times V times F times cosine of the angle divided by C, propagation speed. So this is how I write the formula. I don't write velocity of blood. I don't write transmitted frequency or transducer frequency. I don't write propagation speed. And this is the cosine of theta, so the angle. All right. Remember for this, okay, this is a formula that you have to know. No and ifs or buts about it. You have to know this formula, okay? So please, this is one of those other ones that you have to know. And once you know this formula, you can figure out relationships, because you all should know how to read the formulas by now, right? Um, Velocity, frequency, and cosine of the angle are all directly related to Doppler shift, okay? And then propagation speed is inversely related to Doppler shift, okay? And remember that these guys do not have a relationship with each other, okay? Because they're on the same side. The only things that get affected are things that are on the other side of the equal sign, okay? So from there, you can figure out all the relationships that you need to know here. Now, what you have to then keep in mind is the definition of Doppler shift, which I said earlier was your movement. Okay. Now we're going to expand a little bit on this. Your Doppler shift is your color, and your Doppler shift is your waveform. Okay. So whenever you see color, it's coming from the Doppler shift formula. Okay, so if the Doppler shift formula changes, your color changes. Whenever you see a waveform, that waveform is your Doppler shift. So it's coming from this formula. So if I change something in the Doppler shift, I change my waveform. Okay, those are not independent things. Your waveform is not one thing and your Doppler shift is another. No, it is the same information derived from your Doppler shift. It's simply presented to you differently. Like I can give you a page on statistics, or I can give you bar graphs and pie charts to make it look nicer. And it will still be the same information, right? I just made it look, I illustrated it differently. So this Doppler shift, this is where it all begins. And then it gets shown to you as color or as a waveform. All right. You're not changing the waveform and nothing else. No, no, no. The Doppler shift is changing. And then that's changing your waveform. Okay. So the waveform is just a result of the Doppler shift. That is not like the origin of things. And it's very important because when you start talking about aliasing and when you start talking about seeing color and stuff like that, that is your Doppler shift. If you have a 0 Doppler shift, you have no color and you have no waveform because you have no movement. Okay, and you can make your Doppler shift 0. Okay, and then that's what we're going to talk about in a bit. So in this formula, definitely know the formula and definitely know the relationships in this formula. Okay. The only one that's a little bit tricky is the cosine of the angle. Now, the cosine of the angle is directly related to the Doppler shift. The thing is, you are never going to be given the cosine value of the angle. The exam is not going to say, oh, your cosine was this, and now your cosine is this. Did it go up or did it go down? It doesn't say that. Instead, they give you angles, and they'll tell you your angle went up or your angle went down. And if you make the mistake of saying, oh, my angle went down, okay, so my angle went down, my Doppler shift went down. That is not true, okay? Because the formula is not angle. The formula isn't 2 times V times F times angle, right? Because if it were, it would say this. Instead, it is the cosine of the angle. So if your angle goes up or down, that's fine. But what happens to the cosine value? Okay. There are 3 angles that you should know: 90, 60, and 0. These are the 3 angles that you should know. And these 3 angles have a cosine value attached to each of them. And it's a very simple numbers. 90 degrees is 0. 60 degrees is 0.5. And 0 degrees is 1. So they're all within 0.5 of each other. That's all it is. 0.5 of each other, from 0 to 1. Okay, so your job is to remember that 90 is 0, and that 0 degrees is 1, and 60 is in the middle. And if they're all 0.5 of each other, then you'll remember that 60 degrees is 0.5. So know these 3 angles. All right. It's very important to know them because it gives you a place to start. Now they can ask about your angle changing in 2 different ways. They can tell you that your angle went up or increased. And they can say that maybe you were at 30 degrees and then your angle went up, increased. So in one instance, they don't give you an angle, they just say that it went up. In the other instance, they'll give you an angle and then they'll say that it went up. And for the sake of argument, I'm just picking going up, but they can just ask you going down. All right. But you don't have to know both. Okay. If you know one, you can figure out the other. So let's do the first one. Your angle went up. All right. And this is probably the toughest one because if you never encounter a question like this, which is why it's important to do practice questions. If you never encounter a question like this, it starts to freak you out because then you ask yourself, well, what angle went up? Like, where do I start? It's kind of like, what's going on here? So this is why it's good to know these 3 angles, because if you know these 3 angles, you can pick one and you can make that your start. So I tell students to always pick 60 degrees as your start. Okay, because if 60 degrees is in the center. So if you get asked a question that says your angle goes up, you pick 60 and you make it go up to 90. And vice versa. If you're asked a question where your angle goes down, you pick 60 and you make it go down to 0 degrees. All right, so pick 60. If you pick anything else, I can't help you. Okay, if you pick 0 as your favorite and they say your angle goes down, good luck. I don't know what other angle. I don't know what angle is down from 0 degrees. I know it's going to be a negative angle, but I don't know the cosine value of it, you know? And the same thing with 90. If you pick 90 and it says go up, yeah, you can go up to a lot of angles after 90, but I don't know the values of it. Okay, so you pick 60. So in the first example where they don't give you an angle and they just said it went up, you say, all right, I'm going to pick 60. I'm going to take his advice and pick 60. Then I have to make it go up. I make it go up to my next one, 90. Okay, so this is what I did. I started at 60, I made it go up to 90. Now I need to know what happened to my cosine value. The cosine value of 60 degrees is 0.5. The cosine value of 90 is 0. So this is what I'm looking at. What happened to my cosine? Did my cosine go up or did my cosine go down? And in this case, I started with 50 cents and I'm left with nothing. So my cosine value went down. So now I can go to my formula and say, if my angle goes up, my value goes down. And therefore my Doppler shift goes down. This makes sense? Okay. Remember, if you have any questions, please ask me. The second example is going to give you an angle. So they're going to start at 30 and then they just say go up. Okay. Now, I don't know the value of 30 degrees. All right, but we can always make an educated guess if we have enough pieces in the puzzle. So 30 degrees is in between 0 degrees and 60 degrees. Somewhere in here is 30, right? So somewhere in here is 30 degrees. And 30 degrees, because it's somewhere in between, that means that 30 degrees, the value of it will be somewhere in between 1 and 0.5. Somewhere in between here will be the value of 30 degrees. I don't need to know the value because we're not doing any math. But if I want to just pick something in between between 1 and 0.5. So let's just pick 0.75. That's in between 1 and 0.5. And that's really all I'm concerned about. It's picking some sort of value so that I have like I'm grounded, right? Like I feel like I have a place to start. And now it says your angle went up. So you make it go up. Don't make it go up to 60 degrees. It's like a little too close for comfort. Okay, go to the extreme so that the difference is a lot more obvious, so that you don't start doubting yourself. So make it go up to 90 degrees. And 90 degrees has a value, again, of 0. So I asked myself, what happened to my cosine value? I had 75 cents, and now I have 0 cents. My value went down. So again, cosine value goes down, my Doppler shift goes down. And what does this mean for my color and my waveform? It means that I will see less color. It means that my waveform will be smaller because my shift, my movement is now considered less. Okay. Now let me highlight how important angles are, because in chapter 20 we start off with angles. Angles are so important because let's do some simple math. I'm going to replace all of these guys with very simple numbers. And I'm going to do the cosine of 0 degrees. And I'm going to divide it by the propagation speed, which again, simple numbers. I'm going to make it 1. And in the other example, same thing, but instead I'm going to do the cosine of 90 degrees. And I'm going to divide it by the propagation speed of 1 to keep it simple. So the cosine of 0 degrees is 1. The cosine of 90 degrees is 0. And if I do the math, 2 times 1 times 1 times 1 divided by 1, my answer is 2. This is my answer. And in the other one, 2 times 1 times 1 times 0 divided by 1, my answer is 0. There's my answer. So this could be the exact same vessel on the exact same patient, just seconds apart from each other. And because you change your angle from 0 degrees to 90 degrees, in one example, you saw a Doppler shift, which means you saw color and you saw a waveform. In the other example, you saw nothing. You made it look like there was no movement in that vessel. okay? The machine does not say, wait. Just 2 seconds ago, there was blood moving through here. What do you mean? No, the machine doesn't say that. It only knows math. That's it. It only knows that the angle is now 90. Okay, that's where you come in as the tech to use your common sense and say, wait, there was movement here before. Why is there no movement now? Let me check my angle. Let me check my color box steering. Let me check the vessel. You start checking certain things. All right. But that's the importance of angle. That's the importance of angles. So remember those three angles and the associated cosine values. They will make a difference. And anytime you have a question where the angle goes up and angle goes down, you do this. You start doing little arrows to show you the relationship. Okay. And the other takeaway is that your Doppler shift is your color. Your Doppler shift is your waveform. When we get to aliasing, that will come back a bit more. The best angle is 0 degrees. The worst angle is 90 degrees. This is considered parallel to flow. You're going in the same direction as flow. And this is considered perpendicular to flow. And we'll talk about 90 again, okay? But it's perpendicular versus parallel, right? Fun fact, when you are in Doppler, right? When you're in Doppler looking at movement, this is what you want. But when you are doing 2D imaging, not Doppler, just your regular grayscale 2D imaging, you actually want this, 90 degrees, okay? So when you're in Doppler, you want to be going with the flow. When you are in 2D imaging, you actually want your tissue to be, you want to strike your tissue at a 90-degree angle. So your tissue is like this, and you're striking your beam like that, straight down, and that right there creates 90 degrees. Because it offers like normal incidence, so a stronger reflection. And because we're looking at imaging, we want stronger reflections. Okay, so scanning tip, if you're ever looking at something in the body and it's on the side, move it towards the center. That way you can get a perpendicular incidence to it and it can look brighter and bolder. You can get more detail out of it. Okay, and obviously you do that by rocking your transducer or moving your transducer. Okay. Now they want you to know this term. This term is called phase quadrature detection. Okay, this term, and it just basically means bidirectional Doppler. So bi is 2 and then directional is directions. So you can see 2 directions. Okay, this is what allows us to see 2 directions. And they can ask you a question about this where they give you the definition and they want you to give them the term, or they can give you the term and they want you to give them the definition. Like, what allows us to see 2 directions? Bidirectional Doppler. What is phase quadrature detection? Allows us to see 2 directions. So they can ask you either way. Okay, and this is very important because a lot of pathology comes from being able to see 2 directions. In echo, we have something called regurgitation. And this can only be seen if we can see 2 directions, because regurg is when something goes the opposite direction. So we see the direction it's supposed to, and then we see the little leak going backwards. Okay, so you normally get this. This will be the normal coming towards us, let's say, and then this will be the leak right here, going away from us. Okay. In abdomen, for the portal vein, that could be another example because the portal vein is supposed to be hepatopedal flow, not hepatofugal flow. So how do you know it's how do you know that it's hepatopedal? Well, you know that it's moving towards you based on your velocity map, and we'll talk about that later. But you know that this color up here is towards you. So if you see that color, you're happy. But all of a sudden you see that color, and then the next second you see this color. Well, the fact that you can see both tells you can see two directions. Okay, so they just want you to know this term. That's all, nothing else. Now let's get into some continuous wave versus pulse wave. And these two guys are opposites of each other. Okay, complete opposites. This guy has two crystals to do one job. This guy has one crystal to do two jobs. So already they're beginning opposites. Even in the name, one is continuous and one is pulse. A pulse has a break in between, right? So if you put your index finger and your middle finger over your carotid and you feel your pulse, there is a break. It's like boom, boom, boom. It's not brrr, right? It's just boom, boom. There's a break. There's a break in between. Okay, that's a pulse. Versus continuous, there is no break. That's why a continuous wave is like this. Continuous, doesn't stop. And a pulse is like this. Break, break, break. Okay, so they look different in every sense of the word. Now, when it comes to Doppler and damping material, they have some differences. So we'll cover both of them now. Everything that has an advantage has a disadvantage. Okay, so it's um, a very nice way to look at things, not just in physics and science, but like, in general in life, right? If we want to get philosophical, everything that has an advantage has a disadvantage. So, funny, funny story. Um, so I'm a pretty calm guy. I don't really raise my voice. I mean, of course, we all have a temper, but even when I have a temper, I'm pretty chill about it. Okay, so I'm if we are in a relationship, I'm not the person to argue with, because usually in relationships, at least from what I know, when you argue, you want to see a reaction out of the other person, right? That they're getting upset, that they're being bothered, and when they don't, you get more upset, right? At least that's that's what I've noticed. Okay, so I'm really just not, right. Like I'll get upset and be like, damn man, yeah, that's very upsetting, whatever, whatever. But we're not gonna have a shouting match. It's just not gonna happen. Not this is not VH1. No shouting matches over here. So one time, this person was just this girl I was seeing. She just was upset at me. Like things weren't working out, and she was just upset at me. And I wasn't laughing or anything. I was just there listening. She was telling me this, and that, and I was like, listen, yeah, I'm sorry. Like I'm just, that's it. Like I wasn't defending myself or anything like that, because I felt like there was nothing to defend. That was just the way things are. And she just kept throwing jabs and jabs and jabs until something sticks, right? So she comes up with this little piece of nugget gold right here. And she and we talk every once in a while, and I bring it up and she just starts laughing. She said, You, you and your stupid Buddhist face. And I was like, what? And I got upset. And that actually did it. I got upset and I walked up and I left. But I was like, who the heck says that? So anyway, it was pretty funny. So anything that has an advantage has a disadvantage. Even though I could be great at communicating and explaining, sometimes that can be a disadvantage, right? When you just want that raw, like emotional reaction. So anyway, so all of that just to get into this. A continuous wave has an advantage and continuous wave has a disadvantage. All right. The advantage of continuous wave is that it measures high velocities accurately. It actually measures all velocities accurately, but one of the biggest advantages, the focus, is that nothing is too fast for continuous wave. Okay. Because of that, we say that there is no aliasing. Okay, and aliasing is the next topic. So there's no aliasing in there. Okay, now what is the at disadvantage? What is the disadvantage? The disadvantage is something called range ambiguity. Okay, ambiguity means ambiguous. Ambiguous means it's not really certain, like it's unsure. Okay, and then range, this is the part where it can get a little confusing because you have range resolution, but range resolution can either be from the range equation, which is the 13 microsecond rule, or range resolution from LARD, which is the axial resolution. Okay, so in this case, they're talking about the 13 microsecond rule, which is where things are, essentially the location of things, because that is what the range equation tells you. Every 13 microseconds, you're 1 centimeter away. That is your location. You're 1 centimeter away. So when you put these two things together, it just means that it is unsure of its location. Okay, that is range ambiguity. And what does that mean? It means that if I have two vessels and I run a continuous wave through them, and I start getting my wave, okay, the wave repeating itself, you cannot tell me where this wave is coming from. Out of these two vessels, you cannot tell me because it's because of range ambiguity. Okay, so theoretically, you cannot tell me. Now, we normally don't see this as much of an issue because we use color and then we use continuous wave. Okay, and then we'll talk about why color um, in this case figures things out. Okay, that's actually for Friday. But we use color and then we use continuous wave. So color pinpoints where the fastest velocity is, and then we use continuous wave. So when we look at this wave right here, if we already use color and we know that the fastest is coming from here, right? When we see this wave, we know that the fastest, which are the peaks, are coming from here. But that's only because color Doppler already told us that, okay? But if I were to not use color Doppler and then just put continuous wave, I wouldn't know where these peaks are coming from. I wouldn't know if it's from there or if it's from up here. I wouldn't be able to because of the range ambiguity, okay? But again, this is more for the exam. In real life, we kind of work the ways around it. In Echo, we use continuous wave everywhere. But we always have an idea of where our fastest velocities are because we use color. So the moment that we know where our fastest velocities are and we put a continuous wave running through there, we know that the fastest part of that wave is from that exact location that we already, pinpointed. All right. So what we do here is that we take the advantage and we turn it into, what we do here is that we take the disadvantage and we flip it. We turn it to an advantage. The word itself, we just flip it. Disadvantage becomes advantage. So then we do the same for the bottom. If we're going to flip the name, let's flip what falls underneath it. So underneath it falls range ambiguity, which is a bad thing. But if I'm doing an advantage, I need to flip that and make it into a good thing. And that would be called range resolution. Another term is range specificity, right? Which just means it's specific. That's it. And then range is location. So now we are being very specific about the location. Or we have resolution, which is accuracy. So we are being accurate about its location, which is the opposite of range ambiguity, okay? And how do we achieve that? Sample gate. That's how we achieve it. Because now if I have two vessels and I run a pulse wave through them, guess what I have now? A sample gate. And the only thing I'm going to see is whatever runs through the sample gate. So the moment I start seeing this, This wave that's repeating itself is only the blood that is coming through the sample gate. Nothing else. Not the blood on this side, not the blood on this side, not the blood over here, not the blood over here. Nope. Only the blood that is running through this sample gate. That's the only thing I'm going to see. That's why they call it a sample, right? When you sample something, you take a little piece of it. Okay? And I can move this sample gate around. And anytime I move it around, I know exactly where it is. I know exactly where it is. And that is the whole concept of range resolution, you knowing the location, okay? If you recall, continuous wave, no sample gate. It doesn't have a sample gate, it just has a cursor line running through it. Okay, no sample gate. So then we do the same for the advantage of continuous wave. We take that word and we flip it, which makes it a disadvantage. And now we take underneath it and make it into a disadvantage. So before we had no aliasing, now we are subject to aliasing. And subject to aliasing means that it can happen. Not that it always will, but it can happen if the circumstances are right. For a continuous wave, does not matter. I don't care if the circumstances are right. It is not happening. Okay, so that's what continuous wave is promising you. I don't care how fast that blood is going. It's never going to be aliasing. Okay, whereas pulse wave says, well, hold on there. If it's fast enough, well, yeah, maybe it will be aliasing. If it's slow, I can deal with it. But if it's fast enough, then I don't think I can. So it's subject to aliasing. Does this make sense? Okay. Good. So it's just the opposites, okay? And this, we'll see the same thing again now that we talk about damping material. So pulse wave has damping material, which is called the backing material. Continuous wave, no damping material, no backing material. And this already sets the stage. One has it, the other one doesn't. So that tells you, oh, they're opposites. One has it and the other one doesn't. They're opposites. What you need to remember about damping material or backing material is who has it, right? Pulse wave. Who doesn't have it? Continuous wave. And the three consequences associated with them, because they can just ask you little questions about this. And it's no more than just, you know, what is a consequence of backing material? What if you have backing material, you know, what does it mean that you're going to have? Like, what else are you going to have? Like the little definitions, okay? Nothing, nothing beyond that. So if you have a backing material, you have a wide bandwidth, which means many frequencies. That's what it means, many frequencies. You also have a decreased sensitivity, and you have a low quality or Q factor. Now, wide bandwidth means many frequencies. Any imaging transducer, so any transducer that creates an image, is a wide bandwidth transducer. If you ever look at the side of your transducer, when you turn it on its side, you'll see numbers printed on them. They're going to be printed in the same color as the transducer, so it's not going to stand out. It's almost like if it's what's the word? Like braille on the on the transducer itself. And the curve, for instance, yeah, it's going to be incognito, but it's going to be like raised on the transducer itself for sure. So you'll see the number there, unless I think the curve is 10 to 5. And what it's telling you is that this transducer can go up to 10 megahertz or down to 5 and anything in between. So it's giving you a range. It's not just giving you one frequency. It's giving you a range of frequencies. Okay. And this is what allows us to change the frequency of our transducer and say, oh, I need to, and this patient is heavy. Let me click penetration. Let me lower my frequency. Or, oh, I'm doing pediatrics. It's a young kid. Let me up my frequency. Okay. The fact that you can switch means that you have the option to switch because you have frequencies to choose from. So that is a wide bandwidth. Okay. Many frequencies to choose from. Decrease sensitivity. So sensitivity is a big concept in ultrasound. There are two definitions for it. There is the gold standard quality assurance definition for it, okay, which is when you test positive for a disease or a condition. And there's in my review, I have like the little table that you should know to get any question right that deals with that. So that's one definition of sensitivity. The other definition of sensitivity, which is the bigger one, the most common one in ultrasound, is how much you see. Okay. So when it comes to sensitivity, just think about the word sensitivity and think about what it implies when you're referring to someone who is sensitive. If you have someone who is very sensitive, anything you say, anything you do, they'll feel it. They'll catch it, right? Or even what you don't say, it'll affect them. So they'll feel everything, no matter how little. And if someone who is not sensitive, right, they don't feel as much. You can say that they're cold or it just rolls off their shoulder. So when it comes to ultrasound, it's the same idea. In ultrasound, if you are very sensitive in ultrasound, well, we're not feeling, right? But what are we doing? We are seeing. So if you're very sensitive, you're going to see more and more and more and more. And on the other side, if you are less sensitive, you're going to see less. Okay, so when we get into gains specifically and scales, this will come up because your job is to try to figure out what is my problem right now. Am I seeing too much or am I seeing very little? So it's always great to know where to start. If you know what the problem is, then it's easier for you to find a solution. Okay. So if you know that the problem is I am not seeing enough, the solution then becomes, well, see more. Then you ask yourself, how do I see more? What settings do I need to do to make me see more? You know, and then we'll go through gains and scale and I will teach you how you turn up your gain or down your gain and which one will let you see more and which one will let you see less. But it's always very important to just recognize, oh, the problem right now is that I'm not seeing enough. So then that kind of like that gives you the direction. Okay, I need to see more. All right, what will let me see more? Okay, my gain. All right, what should I do to my gain to see more? My scale. What should I do to my scale to see more? My wall filter. What should I do to my wall filter to see more? You know, but at least you have that in the back of your head. See more, see more, see more. All right. So that is decreased sensitivity. So when you have a damping material, you have decreased sensitivity. It just actually works with damping material absorbing reflections, and sometimes the reflections that it absorbs, they get lost in there. They never come out. And every reflection has a piece of information. So if you're going to tell me that some reflections are never going to make it out, that means that there is some piece of information I'm never going to see. Okay, that's why I decrease sensitivity. Some things I'm not going to see. And then low quality factor. Quality factor has a formula that goes along with it. I wouldn't worry about it. Okay, I think it's maybe a little bit more important to know that it belongs here with these two guys. And so I focus more on trying to help you remember that. And the way that I remember low quality factor belongs with decreased sensitivity is because of the word quality. So when I think of something that is high quality, I think of something perfect, flawless. It's high quality. Okay. So if a damping material says, hey, listen, I'm going to give you decreased sensitivity, meaning you're going to miss out on some information. My response is going to be, oh, you must be low quality. Because if you were high quality, I wouldn't be missing out on anything. Okay. So just by looking at that, I would say, oh, you're low quality. So that's the way I try to remember it. That's not the sign. That is not the science behind it. That's just the way that I remember it. Okay. So from here, we create the other guys. Okay. And we just do that by making the opposites. So damping material, no damping material. Wide bandwidth, narrow bandwidth. Few frequencies, or maybe just one. Decreased sensitivity, increased sensitivity. Low quality factor, high quality factor. And look, increased sensitivity, I see everything. Now it's high quality factor. So you don't have to memorize both. Just pick one. Pick one and know that the other guy is the opposite. Does that make sense? Are we good? Are we good? Are we good? Okay. Now let's start aliasing, and this is where we stop. Okay, on the concept of aliasing. So aliasing, this is how I view aliasing. Okay, you have your Doppler shift. You have your Nyquist limit. And then you have aliasing. All right, so this is the ultrasound world. But now let's relate this to the real world. I am driving because it's movement. So the equivalent of Doppler shift for me would be me driving at whatever speed or velocity, right? So 50 miles per hour, that's a Doppler shift. That's a movement, okay? Every time you get into the car, you have to be aware of your speed limit, okay? Now, granted, if you live in the same city for a very long time, if you live in the same neighborhood for a very long time, you don't worry about the speed limit because you already know it. You already know that neighborhoods are this much, highways are this much, so you don't worry too much about it, okay? But if you were somewhere you were never before, the moment you get in the car, you start being cautious about how fast you're going, you know, because you don't know the rules. You don't know what the speed limit is. So anytime I get in the car, I am concerned about the speed limit. And let's say that in this example, my speed limit is 45 miles per hour. So I am driving at 50 miles per hour and my speed limit is 45 miles per hour. In this scenario, I am speeding. Okay, because my driving, my movement is going above my limit. So I am going faster than what the speed limit says I should go. Okay, so I am going over my limit. That is this guy. I mean, that are these guys. Okay, if your Doppler shift is faster than your limit, they call it a Nyquist limit, then instead of speeding, you get aliasing. Okay, aliasing is an artifact, something that you don't want to get. So that is all your, that's how your Doppler shift, your Nyquist limit, and your aliasing relate. Okay, your Nyquist limit is simply your limit. It's how much you can handle. And if you go over that, there's a consequence. That consequence is called aliasing. Okay, so what you really have to remember is what is going over your limit. It's your Doppler shift. Okay, your Doppler shift is the one that is going over your limit. Okay, because this is your movement and this is the limit that there should be on the movement. Okay, if you're under the limit, you're good. That's just like you driving under the speed limit. You're good. There's no speeding, there's no aliasing. But if you go over that, then you have aliasing. So this is the other formula that you should definitely know, the Nyquist limit. So I already said the Doppler shift you must know. You must also know the Nyquist limit, and that is PRF divided by 2. And because it's on top, they're directly related. Nyquist limit is directly related to your PRF. Okay. All right, that is it. In the next chapter, excuse me, in our next session, I am going to discuss the remaining part of chapter 19, which is, yeah, it didn't feel that bad actually. It actually didn't. I think I'm thinking about my weekend crams where I do the entire chapter at once in 2 hours. Then we take a 1 hour break and then I go back and I do chapter 20. So I think I'm thinking more about that, but breaking it up into 1 hour is not so bad. I haven't broken up in 1 hour in a while. All right, so let me stop the recording here.